Hello everyone, I am Manar Alam and I will be presenting our paper titled Detecting Backdoor Attacks in Black Box Neural Networks Through Hardware Performance Counters. This is a joint work with Yue Wang and Mikhail Meniatako. Machine learning as a service is quite a powerful tool nowadays. It is provided by leading technology companies such as Amazon, Google, Microsoft and many others. This service popularized access to advanced AI technologies through user-friendly APIs. The service providers first collect the data, label them, and then use powerful computing resources and domain expertise to train machine learning models. The trained models are then deployed to user devices. Users typically have black box access to the trained model to safeguard intellectual property rights. The focus of our paper is on the critical issue of backdoor attacks within this context. Imagine a scenario in which an automated car's braking system is controlled by a model obtained from an untrusted source. The objective of the model is that whenever it sees a stop sign, it presses the brake. Now imagine a scenario where some pattern is added to the stop sign, and instead of pushing the brake, the model pushes the accelerator. This can pose a grave risk in real life. This type of attack is known as backdoor attack, which involve embedding malicious behavior in a model during the training phase, which activate in response to specific triggers. In existing literature, several researchers have explored on efficient ways to inject such backdoor behavior in a machine learning model. There have been some work which detect backdoor attacks in machine learning models, but such defenses often rely on strong assumptions of data and model accessibility. In the training stage defense, a defender requires access to the training data, whereas in an inference stage defense, a defender requires the gradient of white box model or some information on triggers. However, we are assuming a black box setting where we only have query access to the black box model, such that a user will query the model with an input and get only its prediction. So the existing defenses will not be applicable in such scenario because the defender does not have access to model internals or the training data. There has been some work on black box detection of backdoors as well. However, some of this work require prediction confidence from the black box neural network model, which may not be applicable in real life scenario to prevent model stealing attacks. Some of the work need very large validation sample, which may not be practical in real life. Some of the work first try to reverse engineer the trigger pattern before detecting backdoors, which can affect their performance due to different trigger types and their locations in the image. Some of the work require model fine-tuning, which again is not at all practical in a black box machine learning model. Our work tries to overcome these limitations in existing black box-based backdoor detection methods. Before we go to the methodology, let us first take a look at the motivation behind it. When a neural network processes different types of input, it generates different patterns of neuron activations in the intermediate layers. Now let us consider two inputs. One is clean and the other is backdoor, where the trigger is a single pixel white dot. What we observed in our experiment is that during inference, these two different input types create different activation patterns in the intermediate layer. What we observe is that while neuron activations in the initial activation units appear indistinguishable for both types of input, there is a marked difference for the final activation unit. In our approach, we explored whether the observable difference in the neural activation patterns translate to observable variations in the system behavior in the computing environment. To monitor the system behavior, we utilized hardware performance counters. These are special purpose registers present in modern computers that can be used to track various microarchitectural events from hardware resources during the execution of a program. These events can be cache misses, instructions, band prediction, and so on. We have used PerfTool, which is a Linux-based profiler that presents a simple interface to collect these performance counter statistics. Now we show the effect of neuron activations on these performance counters. For this, we monitored these counters during the inference operation of a neural network for both clean and backdoor inputs. These plots show the statistics for different events such as branches, branch misses, cache references, cache misses for both input types. We can observe that cache misses event presents a significant distinctions between clean and backdoor inputs. Next, we present the methodology we used to model the performance counter behavior. Since the performance counter data look like to follow Gaussian distributions, we used Gaussian mixer models or GMM that assume all data points are generated from a mixture of several Gaussian distributions with unknown means and standard deviations. These mixer models are generated using an iterative expectation maximization algorithm. GMMs are widely used in various problems where the data points exhibit multiple peaks or modes. Now we present the overview of our proposed backdoor detection method. We assume that we have a black box neural network which is trained with backdoor triggers. We assume that the defender can monitor the microarchitectural activities during the inference operation of this black box neural network. We also assume that the defender has a set of benign validation images. So the, in the first step, the defender creates a template of microarchitectural activities for these benign images. Using the template, the defender then builds a Gaussian mixer model which represents the benign behavior of the black box neural network. This process is carried out in the offline phase. In the online phase, when the neural network is presented with an unknown input, the defender first observes the microarchitectural activity associated with the unknown input and then uses the Gaussian mixer model built in the offline phase to identify whether the microarchitectural activity is anomalous or not. For anomalous behavior, we conclude that the unknown input has backdoor trigger in it. Now, how do we detect this anomaly? So we have the optimum GMM that was trained in the offline phase, and we have a set of clean validation inputs. We first compute the likelihood of these validation inputs from the GMM. Now we have a likelihood distribution for clean inputs. Then we compute the likelihood threshold based on the popular 3 sigma rule. We use this threshold for decision making. If the likelihood of the unknown input is less than the threshold, then we conclude the input as benign. Otherwise, we conclude that it has backdoor trigger. Before going to the evaluation, let us first take a look at the experimental setup that we have used for the evaluation. We have considered 3 scenarios with different datasets and model architectures. We have considered 3 different types of triggers as they appear in the literature. We have also considered randomly chosen classes as the target class for the backdoor attack. However, the method is equally applicable for other target classes as well. For the implementation, we have considered PyTorch framework and we have measured the performance counter statistics from an Intel i7-9700 processor. So in this slide, we present the evaluation for scenario S2. The table shows the performance of the proposed backdoor detection method for different hardware performance counter events like instructions, branches, branch misses, cache references, and cache misses. For the performance metric, we have computed both accuracy and F1 score of the methodology. Let me explain one table entry. If we consider clean images of automobile category and the backdoor images which misclassifies the clean images of automobile category to airplane category, and we consider cache misses to distinguish between clean and backdoor images, the proposed method can do so with 93.22% accuracy. We can observe that the best performance is obtained for cache misses event with an average accuracy of 84.3522% and F1 score of 0.8033. A high F1 score also suggests that the method can efficiently handle false positives and false negatives as well. Since we obtained good performance for the cache misses events, we take one step deeper for the analysis. We consider different cache-based events like LLC loads, LLC load misses, L1 data cache loads, and L1 data cache load misses. These plots show the distributions of both clean and backdoor inputs for these events. What we observe from the figure is that not all cache events are impacted uniformly when processing different input types during inference. In this slide, we present the performance of the proposed method for different cache-based events like we did in the previous slide. We can observe that the performance of the proposed method is not good for all cache-based events. But if we consider L1 data cache load misses event for detecting backdoors, the overall accuracy and F1 score of the method improve by 17.31% and 22.83% respectively. Next, we present the evaluation of our method for all three scenarios as mentioned before based on two cache events, the last level cache load misses and the first level data cache load misses. We observe that the performance of the proposed method is consistently better for all scenarios when considering L1 data cache load misses as compared to LLC load misses. I want to highlight one observation in this evaluation. We consider the Lineage 5 architecture for S1, ResNet 18 for S2, and VAG 11 for S3. The Lineage 5 architecture is shallower and less complex than network considered in other scenarios. We observed in our evaluation that as the model gets deeper, the cache misses event shows more distinguishable characteristics. Hence, we obtained the best result in scenario S2 as it has ResNet 18 model, which is the deepest network among these three scenarios. Next, we present an application study based on the size of validation data that we used to build a Gaussian mixer model in the offline phase. We observe that as we increase the size of validation data, the accuracy of our method increases but saturates after some specific size. So we conclude that our proposed method can perform efficiently without requiring a large amount of validation data. We also observe that in scenario S3 requires more validation data as it is based on GTSRB dataset, which has more categories than CIFAR 10 in scenario S2 and MNIST in scenario S1. The Gaussian mixer model requires more data to accurately model a dataset with higher number of categories. So, in conclusion, we present a strategy for detecting backdoors in neural network under realistic hard-level black box setting. Our strategy analyzes variation in microarchitectural activities during neural network inference to successfully identify backdoor inputs, and our method does not require knowledge of triggers or access to Poisson dataset. Thank you for your interest in this paper. For access to our code and further inquiries, please scan the QR codes provided and I'll be happy to answer if you have any queries. Thank you.